6.4 Graphs of logarithmic functions. In graphs of exponential functions, we saw how creating a graphical representation of an exponential model gives us another layer of insight for predicting future events. How do logarithmic graphs give us insight into situations? Because every logarithmic function is the inverse function of an exponential function, we could think of every output on a logarithmic graph as the input for the corresponding inverse exponential equation. In other words, logarithms give the cause for an effect. To illustrate, suppose we invest $2,500 in an account that offers an annual interest rate of 5% compounded continuously. We already know that the balance in our account for any year t can be found with the equation a equals 2,500 e raised to the 0.05 t power. But what if we wanted to know the year for any balance? We would need to create a corresponding new function by interchanging the input and output. Thus, we would need to create a logarithmic model for this situation. By graphing the model, we can see the output year for any input account balance. And for instance, what if we wanted to know how many years it would take for our initial investment to double? Figure 1 shows this point on the logarithmic graph. In this section, we will discuss the values for which a logarithmic function is defined, and then turn our attention to graphing the family of logarithmic functions. Finding the domain of a logarithmic function. Before working with graphs, we will take a look at the domain, the set of input values for which the logarithmic function is defined. Recall that the exponential function is defined as y equals b of x for any real number x and constant b greater than 0, b not equal to 1, where the domain of y is negative infinity to infinity, and the range of y is 0 to infinity. In the last section, we learned that the logarithmic function y equals log base b of x is the inverse of the exponential function y equals b of x. So as inverse functions, the domain of y equals log base b of x is the range of y equals b of x, 0 to infinity. The range of y equals log base b of x is the domain of y equals b of x, negative infinity to infinity. Transformations of the parent function y equals log base b behave similarly to those of other functions. Just as with other parent functions, we can apply the 4 types of transformations: shifts, stretches, compressions, and reflections to the parent function without loss of shape. In the graphs of the exponential functions, we saw that certain transformations can change the range of y equals b of x, and similarly, applying transformations to the parent function y equals log base b of x can change the domain. When finding the domain of a logarithmic function, therefore, it is important to remember that the domain consists only of positive real numbers. That is, the argument of the logarithmic function must be greater than 0. For example, consider f of x equals log base 4 of 2 of x minus 3. This function is defined for any values of x such that the argument is this case, 2x minus 3, is greater than 0. To find the domain, we set up an inequality and solve for x. 2x minus 3 is greater than 0 and show the argument greater than 0. 2x greater than 3, add 3, and x greater than 1.5, divide by 2. In interval notation, the domain of f of x equals log base 4 of 2x minus 3 is 1.5 to infinity. How to? Given a logarithmic function, identify the domain. 1. Set up an inequality showing the argument greater than 0. 2. Solve for x. And 3. Write the domain in interval notation. Graphing logarithmic functions. Now that we have a feel for the set of values for which a logarithmic function is defined, we move on to graphing logarithmic functions. The family of logarithmic functions includes the parent function y equals log base b of x, along with all its transformations, shifts, stretches, compressions, and reflections. We begin with the parent function y equals log base b of x because every logarithmic function of this form is the inverse of an exponential function with the form y equals b of x. Their graphs will be reflections of each other across the line y equals x. To illustrate this, we can observe the relationship between the input and output values of y equals 2 to the x power and its equivalent x equals log base 2 of y in table 1. Using the inputs and outputs from table 1, we can build another table to observe the relationship between points on the graphs of the inverse functions f of x equals 2 to the x power and g of x equals log base 2 of x. See table 2. As we'd expect, the x and y coordinates are reversed for the inverse functions. Figure 2 shows the graph of f and g, and observe the following from the graph. F of x equals 2 raised to the x power has a y-intercept at 0, 1, and g of x equals log base 2 of x has an x-intercept at 1, 0. The domain of f of x equals 2 to the x power and negative to infinity is the same as the range of g of x equals log base 2 of x. The range of f of x equals 2 to the x power, 0 to infinity is the same as domain of g of x equals log base 2 of x. Characteristics of the graph of the parent function f of x equals log base b of x. For any real number x and constant b greater than 0, b does not equal 1, we can see the following characteristics in the graph of f of x equals log base b of x. One-to-one function, vertical asymptote where x equals 0. The domain is 0 to infinity. The range is negative infinity to infinity. X-intercept is at the coordinate point 1, 0, and the key point is at b1. The y-intercept is none. It's increasing if b is greater than 1. It's decreasing if 0 is less than b less than 1. Please see figure 3. Figure 4 shows how changing the base b in f of x equals log base b of x can affect the graphs. Observe that the graphs compress vertically as the value of the base increases. So note, recall the function, the natural log of x has a base, e is approximately 2.718. How to? Given a logarithmic function with the form f of x equals log base b of x, graph the function. 1. Draw and label the vertical asymptote, x equals 0. 2. Plot the x-intercept at the coordinate point 1, 0. 3. Plot the key point at the point B1. And 4. Draw a smooth curve through the points. And 5. State the domain, 0 to infinity, the range, negative infinity to infinity, and the vertical asymptote, x equals 0. Graphing transformations of logarithmic functions. As we mentioned in the beginning of the section, transformations of logarithmic graphs behave similarly to those of other parent functions. We can shift, stretch, compress, and reflect the parent function y equals log base b of x without loss of shape. Graphing a horizontal shift of f of x equals log base b of x. When a constant c is added to the input of the parent function, f of x equals log base b of x, the result is a horizontal shift c units in the opposite direction of the sign on c. To visualize horizontal shifts, we can observe the general graph of the parent function, f of x equals log base b of x, and for c greater than 0, alongside the shift left. G of x equals log base b of x plus c, and the shift right. H of x equals log base b of x minus c. See figure 6. Horizontal shifts of the parent function y equals log base b of x. For any constant c, the function f of x equals log base b of x plus c. Shifts the parent function y equals log base b of x left c units if c is greater than 0. And shifts the parent function y equals log base b of x right c units if c is less than 0. So has the vertical asymptote, x equals negative c, has domain, negative c to infinity, has the range, negative infinity to infinity. How to? Given a logarithmic function with the form f of x equals log base b of x plus c, graph the translation. 1. Identify the horizontal shift. A, if c is greater than 0, shift the graph of f of x equals log base b of x left c units. B, if c is less than 0, shift the graph of f of x equals log base b of x right c units. 2, draw the vertical asymptote, x equals negative c. 3, identify 3 key points from the parent function. Find new coordinates for the shifted functions by subtracting c from the x-coordinate. 4, label the 3 points. 5, the domain is negative c to infinity. The range is negative infinity to infinity. And the vertical asymptote is x equals negative c. Graphing a vertical shift of y equals log base b of x. When a constant d is added to the parent function f of x equals log base b of x, the result is a vertical shift d units in the direction of the sign on d. To visualize vertical shifts, we can observe the general graph of the parent function f of x equals log base b of x alongside the shift up. G of x equals log base b of x plus d, and the shift down h of x equals log base b of x minus d. See figure 8. Vertical shifts of the parent function y equals log base b of x. For any constant d, the function f of x equals log base b of x plus d shifts the parent function y equals log base b of x up d units if d is greater than 0. It shifts the parent function y equals log base b of x down d units if d is less than 0, has the vertical asymptote at x equals 0, has the domain 0 to infinity, and has the range negative infinity to infinity. How to? Given a logarithmic function with the form f of x equals log base b of x plus d, graph the translation. 1. Identify the vertical shift. A, if d is greater than 0, shift the graph of f of x equals log base b of x up d units. B, if d is less than 0, shift the graph of f of x equals log base b of x down d units. 2. Draw the vertical asymptote at x equals 0. 3. Identify 3 key points from the parent function. Find new coordinates for the shifted functions by adding d to the y coordinate. 4. Label the 3 points. 5. The domain is 0 to infinity. The range is negative infinity to infinity, and the vertical asymptote is x equals 0. Graphing stretches and compressions of y equals log base b of x. When the parent function of f of x equals log base b of x is multiplied by a constant a greater than 0, the result is a vertical stretch or compression of the original graph. To visualize stretches and compressions, we set a greater to 1 and observe the general graph of the parent function f of x equals log base b of x alongside the vertical stretch. G of x equals a log base b of x, and the vertical compression h of x equals 1 over a log base b of x. See figure 10. Vertical stretches and compressions of the parent function y equals log base b of x. For any constant a greater than 1, the function f of x equals a log base b of x. It stretches the parent function y equals log base b of x vertically by a factor of a if a is greater than 1. Compresses the parent function y equals log base b of x vertically by a factor of a if 0 is less than a less than 1. Has the vertical asymptote x equals 0, has the x-intercept at the coordinate point 1, 0, has the domain 0 to infinity, and has the range negative infinity to infinity. How to? Given a logarithmic function with the form f of x equals a log base b of x, where a is greater than 0, graph the translation. 1. Identify the vertical stretch or compressions. A. If the absolute value of a is greater than 1, the graph of f of x equals log base b of x is stretched by a factor of a units. B. If the absolute value of a is less than 1, the parent graph of f of x equals log base b of x is compressed by a factor of a units. 2. Draw the vertical asymptote x equals 0. 3. Identify 3 key points from the parent function. Find new coordinates for the shifted functions by multiplying the y coordinates by a. 4. Label the 3 points. And 5. The domain is 0 to infinity. The range is negative infinity to infinity, and the vertical asymptote is x equals 0. Reflections of the parent function y equals log base b of x. The function f of x equals negative log base b of x. This reflects the parent function y equals log base b of x about the x-axis. It has a domain of 0 to infinity, a range of negative infinity to infinity, and a vertical asymptote x equals 0, which are unchanged from the parent function. The function f of x equals log base b negative x. It reflects the parent function y equals log base b of x about the y-axis and has the domain negative infinity to 0. It has the range negative infinity to infinity and the vertical asymptote x equals 0, which are unchanged from the parent function. How to? Given a logarithmic function with the parent function f of x equals log base b of x, graph a translation. Summarizing translations to the logarithmic function. Now that we have worked with each type of translation for the logarithmic function, we can summarize each table 4 to arrive at the general question for translating exponential functions. Translations of logarithmic functions. All translations of the parent logarithmic function y equals log base b of x have the form f of x equals a log base b of x plus c plus d, where the parent function y equals log base b of x, b greater than 1, is shifted vertically up d units, shifted horizontally to the left c units, stretched vertically by a factor of absolute value of a if the absolute value of a is greater than 0, compressed vertically by a factor of absolute value of a if 0 is less than the absolute value of a less than 1, reflected about the x-axis where a is less than 0, and for f of x equals log of negative x, the graph of the parent function is reflected about the y-axis. Q&A. Is it possible to tell the domain and range and describe the end behavior of a function just by looking at the graph? Well, yes. If we know the function is a general logarithmic function, for example, look at the graph in figure 16. The graph approaches x equals negative 3 or thereabouts more and more closely, so x equals negative 3 is or is very close to the vertical asymptote. It approaches from the right, so the domain is all points to the right, where x such that x is greater than negative 3, and the range, as with all general logarithmic functions, is all real numbers. And we can see the end behavior because the graph does go down as it goes left and up as it goes right. The end behavior is that x, as x approaches negative 3 to the positive exponent, f of x approaches negative infinity, and as x approaches infinity, f of x approaches infinity. Access these online resources for additional instruction and practice with graphing logarithms. Graph an exponential function and logarithmic function, match graphs of exponential and logarithmic functions, and find the domain of logarithmic functions. OpenStacksCollege.org.